Yes, my dear friends and brothers, because children are my brothers. Okay, so today it's my third lecture based on wave optics and interference of waves. Okay, that is interference of waves. Interference. What we mean by interference? Interference is nothing but just a superposition of waves. We know that light has both wave property as well as ray particle properties. So today we are dealing with the wave properties of light. On the basis of wave property, we can discuss interference, then polarization, like that. Some phenomena we can explain on the basis of wave nature. So today I'm taking interference, then a double slit experiment. Actually, in the JE part, we can get a easy question from this part. It's a scoring part. This wave text chapter is a scoring part. So, interference is nothing but just superposition of waves. Suppose we have waves like y1, first wave, a1 sine omega t minus kx sine omega t minus kx. And I have another wave y2. This is a2 sine omega t minus kx plus phi. It is in another phase. We just see here this omega and k are as same. Y means this is coherent sources. I'm just introducing a new word of coherent sources. These coherent sources, same frequency. Just writing here coherent source. Coherent sources, same frequency, same frequency. Then omega will be same. It is in same media. So these two waves are traveling in same media. Then obviously V will be same because of same media. Then then V is equal to omega by k. We have wave equation. Then this k and this omega is constant. This V is constant for same media. Then this k should also be, and this k is also same. So that's why I write this y1 and y2 like this. Y1 is a1 sine omega t minus kx, y2 is equal to a2 sine omega t minus kx plus phi. This coherent sources, same frequency. Coherent sources, actually the definition of coherent source can produce a constant phase difference at a point in space with time. The constant phase difference at a point in space with respect to time, because when the time changes, even if the time is changing, but the phase difference won't change. If you measure at this point, if you measure a phase difference at a time t is equal to 0 second, after time t seconds also, the phase difference of two light rays, phase difference should be the same as time t is equal to 0. Such sources are coherent sources. For the coherent sources, some properties like same frequency. Now we have seen why k is constant, k is also same. So in these are the just coherent sources. Later on, I will some more. I will write the definition of coherent sources. Now, just keep in mind what is coherent sources. Why this k two are same, k and omega. How it is same. Okay. So now the superposition is happening. Resultant amplitude y is equal to y1 plus y2, obviously. So after some calculation, we can write y is equal to a sine omega t minus kx plus delta. Delta is the resultant constant. You just leave that part. Yeah, I'm interested to discuss about the amplitude part. These two is vectorically superposing with an phase difference of phi. Okay, so this A, it is not just A1 plus A2. It is not like that. This A is square root of A1 square plus A2 square plus 2 A1 A2 1 A2 cos phi. It is a vectorical sum. This is a definition of this A. Okay, a1 square plus a2 square plus 2a1 a2 cos phi. Okay, I'm reducing this equation to a condition like a1 equal to a2. Suppose a naught. Okay. Then the resultant amplitude a is equal to 2 a naught cos phi by 2. It is a easy calculation. You can try it. This you replace this a1 by a naught, this a naught here. Then 1 plus cos theta, that is cos theta by 2. You will get equation like this. So now I am discussing about two type of resultants. One is constructive interference. Constructive interference. What do you mean by constructive interference? Constructive interference is when the amplitude, the resultant amplitude, we will get the maximum. Okay? Constructive interference is when the resultant amplitude, after superposition of these two waves, if we get a resultant maximum amplitude, resultant is maximum. Such case is called constructive interference. Okay? So the condition for the maximum amplitude, from here we can see this cos phi factor should be 1. So the condition is cos phi is equal to 1. When the cos factor become 1, cos pi, cos 0 is 1, cos 2 pi is 1, cos 4 pi is 1. So I can write 0, this 2 pi, 4 pi are giving cos phi is 1. Then I can write phi is equal to 2n pi. Phi is equal to 2n pi. This is a condition for constructive interference. When the two waves are at a phase of 2n pi, then that intersecting waves can produce a constructive interference with maximum amplitude. This is a phase difference. You might know the relation between the phase difference and path difference. Phase difference delta pi is equal to 2 pi by lambda into delta x. Here this delta x is path difference. This is nothing but phase difference. phase difference. Okay, so I can write from for the path difference for the constructive interference as, so this delta phi, this 2n pi is equal to 2 pi by lambda, 2 pi by lambda into delta x. I can write cancel this 2 pi 2 pi, so I will get delta x equal to n lambda. Okay, delta x equal to n lambda. This is a path difference for constructive interference. This is a path difference for constructive interference. Okay. Then I want to introduce one more quantity, intensity. We are discussing about waves. So waves have amplitude. How amplitude is related with intensity? Actually, intensity is directly proportional to amplitude square. Okay, then the resultant superposition amplitude is I1, I is equal to I1 plus I2 plus 2 into root of I1, I2, because I is a square. So the equation become I1 plus I2 plus 2 root of I1, I1, I2. Okay. When cos phi is 1, we can write A max. A max is just mod of A1 plus A2. Okay. So when I1 is then I max, we can write I max is root of I1 plus root of I2 per square, because this mod is square root of A1 plus A1 square plus A2 square. Here this root of A1 plus root of A2 the whole square. I max. So what will be the maximum intensity? I max. This is square root of I1 plus square root of I2. Okay. So next point is, what is constructive interference? What is constructive interference? So now we discuss with constructive interference. So next is destructive interference. Destructive interference is when two superposition of waves and the resultant wave has the minimum amplitude. The resultant wave has a minimum amplitude. Such case is called destructive interference. When it will happen, destructive interference? Obviously, let's see the case. Then cos phi is -1. When cos phi is happening, cos pi is -1, cos 3 pi is -1, cos 5 pi is -1. So I can take phi as 2n minus 1 pi, where n is equal to 1, 2, 3, 4, etc. This is a case of destructive interference. Okay, it's a case of destructive interference. It's a destructive interference. It's a destructive interference. Then what is the path difference for this destructive interference? We know delta pi is 2 pi by lambda into delta x. So obviously this 2n minus 1 y is 2 pi by lambda into delta x, and cancel this pi, then obviously the delta x, that is path difference, is 2n minus 1 lambda by 2. Remember this two formula of path difference and phase difference. Delta x 2n minus 1 lambda by 2. This is a condition for the necessary phase difference for destructive interference of waves. If you know these conditions, then I can move to obviously then I can move to that how this destructive and constructive interference can shown in physical. So that is an experiment, Young's double slit experiment. We have developed these theories. How we can show this experimentally? That is Young's double slit experiment. That Young's is a name of that scientist. Okay, Young's double slit experiment. That Young's double slit experiment setup is very simple. It is not as such simple because we have to produce coherent source. Coherent source we already discussed constant phase difference at a point with respect to time. As the time changes, phase difference can't change. That is coherent source. So in order to produce a coherent source, the possible way the Young has did is create slit. Small, if you take a cardboard, by using a blade, you just make a horizontal cut. It's considered as a slit. Then the light waves passing through the slit can produce coherent sources. Actually, while doing that experiment in laboratories, now that already made slits are available in almost all physics labs in colleges. First, we need to create a dark room, and this whole setup should be in a dark room. And then put a point source, then make a slit. Earlier, we have to adjust the slits. Okay, then adjust the slit. Then we are looking through the slit using our spectrometer. We are just measuring the line. This is a procedure that we did in the labs. But I'm just telling this not for any, just getting a curiosity in future. Okay, so this is another color. Okay, Young's double slit experiment. So I am writing as a short Y Young's double slit. Yes, Young's double slit experiment. So in the Young's double slit experiment, the experimental setup is like this. I'm just drawing the experimental setup. Yeah, this is my slit. This is my slit. Okay. I am first time using this pen tab, so whenever I am giving some pressure, it is showing some option. Okay. And I kept my point source here. Point source here, and then I want to keep my screen, a white screen or somewhat a screen here. So after that, I am observing. Hey, where is my point source? This is my point source. Okay, this light rays, this is the center line. Why center line is going like this? The center line, and this slit and the screen with D. In between, there is a small distance D. These are two separation distance. Okay. So light rays are traveling from here reaching this point source, then from here source is moving, it is moving and reaching a point here. Similarly, light wave, light wave is intersecting here. From here, many directions there. So, and from here, the light wave is moving. Here, the light wave is moving. Um, this is my center line. Here, a light ray reaches here. From here, a light ray is going to reach here. Okay, somewhat it pointed here. Okay. Yes, we are continuing that Young's double slit experiment. YD AC. This is my setup. So this is my primary source S, and here a light ray is traveling and it is reaching this part, making S1. Similarly, light ray can reach here. This is my S2. Here, light can S1 and S2. This is my observing point P. This is my center point O. And the distance between this source and the screen is representing with capital D. And between the slits, between this slit, it is D, small d. I'm just measuring as a small d. Okay. So we are expecting there is a phase difference and path difference. So because of that, at a point of P, we are getting, and on the screen we are getting an interference pattern. We don't know what is at exact P. While observing in that experiment, while observing with the with the resolution of microscope or spectroscope, we are just getting some dark band, some bright bands. Bright is intensity is high, dark intensity is very low. Okay. So at this point P, we don't know what is exact. So we are assuming we here somewhat we have a phase shift. So phase difference we are getting a pattern. So I'm just going into the derivation. First of all, just keep in mind this small d is very small, and this with respect to compare d, most probably this will be around in millimeter scale. This will be around in meter scale, 1 or 2 meter. Wavelength is per lambda Armstrong scale. So these three lines are nearly parallel. Okay, this is three just lines are nearly parallel, and the angle which is making this is theta. Here also a horizontal angle theta. Here also a horizontal angle theta. Okay, then I'm just drawing a line uh, here, and I just wonder how much phase is what I just wonder. We can see from the geometry here from S1. From S1 it is reaching to P, and S2 from S2 it is reaching P. There is this S2 ray is travel somewhat more, so there is a path difference. I'm just going to find out how what is the path difference, how much is the path difference. So to get the path difference, I'm drawing a line here. This is my line. So okay, after this line, these two are traveled equal distance. So after this LLI, these two travel equal distance. This this part is extra path traveled by the S2 ray, S2 to P. It is an extra distance traveled by the second ray. What is that? We can use geometry. So this will be 90 minus theta. So this is 90. So this is theta. This angle also should be theta. This is D. Obviously, this delta x. This is I am considering as my delta x. You can write sine theta is delta x by d. So delta x equal to d sine theta. This is my path difference at this case. This path difference can create either maxima or minima. So what was the condition for maxima? That is constructive interference. Yes, we have seen in the first slide condition for maxima or constructive interference is this delta x should be. I will take another slide. So first condition, constructive interference. Interference. This condition is delta x equal to L lambda. The delta x is d sine theta. Okay. Oh, wait. Okay, here theta is very small. Okay, we have to reduce somewhat form here. Here, theta is very small. That is, theta is very small. So I can write sin theta approximately equal to tan theta. Okay. Okay, tan theta. So from the geometry, considering this triangle, I'm going to find this is y. Y means from the central to this p distance. So from this theta, I'm going to find value of tan theta. I'm getting tan theta is y by capital D. Y by capital D. So I can write. So therefore, I can write delta x is equal to d into tan theta. That is dy by d. Just keep in mind. So this is if in some problem or something, if theta is not small, we have to follow delta x is equal to d sine theta. Here, in our assumption, this theta is very small. If theta is very small, go for this. Sine theta is approximately equal to tan theta. then value of tan theta is y by d, or delta x is equal to dy by d. Okay, so condition for maximum. So here I can erase this delta x, that is, we can write y d by capital D is n lambda. Then what will be y? I can find y from here. So n lambda into id. This will be the position of bright spot. Okay, so let assume n can value 0. If it is 0, then it will get central maxima, or n is equal to 1, we will get y can have either 0 or lambda d by d, that is first maxima, or second maxima 2 lambda d by d, or 3 lambda d by d. Is first 0 central maxima, first maxima, second maxima, third maxima, and so on. This is constructive interference. This is condition for constructive interference. And I can get another condition. Condition for destructive interference also. Destructive interference condition. What will be the condition for destructive interference? You know that delta x is equal to 2n minus 1 by 2. So delta x we have got here y d by capital D is 2n minus 1 lambda by 2. Then I will find the position of destructive or dark spot as 2n minus 1 lambda by 2 into capital D by small d. D by 2 into small d. Okay, lambda d into y is equal to n minus 1 lambda d by 2d. This is position of dark spot. Position of dark spot. Okay. So here also you can get n can have value 1. That will be the first dark band. This is, so y will be n is equal to 1, that is 2n minus 1 lambda d by 2d, and 2, that is 3 lambda d by 2d, and then etc. 2 and 3 6 5 by 2 lambda d by d, etc. So this will be the position of destructive interference, that is dark point. If I try to plot this dark band and the white band in the screen, we can get this my axis. Okay, and this is us. Oh, so if I try to plot the intensity versus position of dark and bright fringe, so I will mark as O, a central point. Central point will be the maximum. The maximum value will be 4i0 that can get from the first equation. Condition for maximum interference, it will be 4i0. I think we have it there. So my second right point will be at this point, that is n lambda values, that is lambda d by d, lambda d by d. Here this may another bright point, 2 lambda d by d. In between I have one dark spot. In between I have one dark spot, so it will be somewhat at half, that is lambda d by 2d. Here I can get 3 by 2 lambda d by d. Similarly, here also I can get same positions here, here. So my center will be maximum. This will be my maximum. There is going to be minimum. Then from here it is going to be maximum at this point. Then from there it is going to be minimum. From there again it is getting maximum intensity at this point, and so on. This is my intensity profile. So here also I will get first minima, and then it is going to be maximum. From there it is going to be a minimum profile, and then it is going to be a maximum profile. This will be, if this will be the plot. This is intensity position. This is my center point. This is my first minima, that is intensity is very low. This is my first maxima, intensity is high. This is my second minima, intensity profile is low. This is my second maxima. Hope up to this it is clear. Then I want to introduce another term, fringe width. Fringe width. What do you mean by fringe width? Fringe width is nothing but distance between two consecutive maxima or two consecutive minimum. It should be consecutive, either between two consecutive maxima or between two consecutive minima. Hope it is clear. Either it should be consecutive maxima or it should be a consecutive minima. From figure we can point out, this is my one maxima, this is my another maxima. These two are consecutive maximas, right? After this first maxima, then one is second maxima. What is the separation between these two? That is bright fringe, that is y to b. I am writing position of second bride minus position of first bride. What will be the value? 2 lambda d by 3 minus lambda d by d. It is obviously lambda d by d. Or fringe width, we can say distance between two consecutives minimum also. Here it's a 3 by 2. I will write y 2d, that is second dark minus first dark. Second dark minus first dark. That is 3 by 2 lambda d by d minus lambda d by 2d. Obviously, it is also lambda d by d. I hope it is clear up to this. So, is there any dependence of this lambda? I can write this French term called beta. Beta is the lambda d by d. Okay. So, I just want to point out fringe width depends on. I will make another slide. Fringe width depends on medium. Okay, that is beta is lambda d by d. That is beta is directly proportional to lambda. So beta 1 by beta 2, which is equal to lambda 1 by lambda 2. This lambda is when two different media. Okay, that is refractive index is mu2. mu1 of beta 1 by beta 2 is lambda 1 by lambda 2. This is mu2 by mu1 because lambda is depends upon refractive index of the media. So the new lambda will be lambda by mu. Hope it is clear. That is depends on media. And media means refractive index. Whenever we are talking about light property, we most of the time we just want to care about the refractive index. Okay, so here lambda, when first in the first setup, if we measure somewhat in air, then the whole setup is changed to water. What will happen? Refractive index of the experimental setup was changed. So in that, actually the change is for lambda. And the lambda change is creating fringe with beta accordingly. It is beta 1 by beta 2 is lambda 1 by lambda 2 is proportional to mu2 by mu1. Okay. And in JEE, we can get a question like this. YDXC experiment in water. Okay, YDXC experiment in water. So in air, we will get beta fringe widths in air. beta fringe with is lambda d by d. But if we change it to if we change to water, lambda will shift to lambda by mu. This mu is the refractive index of the water. So in YDSC, the beta will change us to lambda d by mu d. That is beta by mu. Okay. So if YDSC experiment is happening in water, the fringe width will change it to fringe width by refractive index. Okay. Then if it is clear, I will give a question. When the whole, I will write this question here. When the whole YDSC setup, that is Young's double slit experiment setup, is put in liquid of is put in liquid. Okay. Then ninth minima, then ninth minima takes place ninth minima takes place of originally occupied phase takes the place of originally occupied fifth maxima there. Then find refractive index of liquid. Then find refractive index of the liquid. I hope this question is clear. I'll read the question. When the whole YDC setup is put in a liquid, then ninth minima takes place the originally occupied fifth maxima in air. Find the refractive index of the liquid. What here? The whole setup, it is put in a liquid with unknown refractive index. Okay. And what here it is given is when we put that liquid in water, then the ninth minima takes place of fifth maxima, originally occupied fifth maxima, when the setup was in air. Okay, so I can write ninth minima, the position of ninth minima in liquid. Okay, position of ninth minima in liquid equal to fifth maxima in air. Fifth maxima in air. So just we want to put the equation of minima, that is 2n minus 1 lambda d by d, 2n minus 1 lambda d by 2d, lambda d by 2d, and refractive index of mu, which is equal to the maxima in air, that is n lambda d by d. So here n is 9, that is 9 to 8, 8 into 17. This lambda d by d I can put as beta. Lambda d by d into beta by 2 mu, beta by 2 mu, which is equal to 5 beta. This beta will cancel. So we want to find mu. So mu is equal to 17 by 10. That is 1.7. So the refractive index will be 1.7 of the given liquid. I hope to this it is clear. Yeah, okay. Then next part I want to introduce about angular locations of fringes. Fringes is angular locations. We are measured in this figure. I will go to that figure. Okay. Here we have seen in P we either will get a dark fringe or bright fringe, or here we can get either a dark fringe or bright fringe. Here we can get a dark or bright. Anywhere at this point we can get. So when we observe from this point, okay, when we observe how much is the angle with respect to the angle we are seeing, what is the position of the fringe? We are just saying with respect to the fringe, with okay, that fringe location with respect to angle. We are saying with respect to this angle. So we can say angular locations, angular locations. Angular locations is nothing but angular. Okay, we are expressing the position of fringes in terms of angle. So from the figure, it was clear theta is equal to y by capital D. So for a dark fringe, so for bright fringe, y is n lambda d by md. That is n lambda by d. Then for dark fringe, it is theta of dark fringe is 2n minus 1 lambda by 2d. So in general, angular width which is equal to beta. Beta is a fringe width by capital D. Okay, that is d lambda d by capital D. So lambda by d is the fringe width. Lambda by d is the angular fringe width. Angular fringe width is the beta by capital D, that is lambda d by d divided by capital D, so lambda by d. Okay, this is all about the first part of YDSC experiment. Some more modification is there. I will just revise. First we discussed about interference, everything. So then we move on to YDSC experiment. The YDSC experiment, we have seen there is a phase difference of delta x. So the delta x we have found out in terms of positions. That is delta x is dy by d. Then we applied the condition for maximum interference and the minimum interference. So we are getting some points. In these points we will get maximum intensity, and these points we will get minimum intensities. Then we move on to the positioning of these images. We are plotting in graph or any software at these positions, that is lambda d by d or 2 lambda d by d, we will get maximum bright fringe, or lambda d by 2d or 3 by 2 lambda d by d. In between the positions we will get minimum intensity dark field. Then we have introduced a term of fringe width. What is fringe width? It is distance between to either two consecutive maxima or between consecutive minima. So we have found the expression for beta is lambda d by d. Then we move on to dependence of beta with respect to different media. That is basically it depends on the mu refractive index. Then we have seen a problem. Then we move on the angular locations and angular fringe width of YDSC experiment. So the first part is over here. We will do a problem from this. Okay, so just in an young, I will read the question. In a young double slit experiment, the slits are 2 millimeter apart and are illuminated by photons of wavelengths of lambda 1 by 12,000 and lambda 2 by 10,000. What minimum distance from the common central bright fringe on the screen 2 meters from the slit will be a bright fringe from one interference pattern coincide with the bright fringe from the other? Okay, actually it's a question. I put this question for realizing the values of capital D, small d, wavelength, and crop. Here you can see the slits are 2 millimeter apart. 2 millimeter. Okay. And print on the screen, capital D, 2 meter. Just see the difference. 2 millimeter to 2 meter. That's why we took first assumption. The slit between the slit, the distance should be millimeter range and capital D in meters. Okay, wavelength lambda 1, lambda 2. Okay, now we will go to the question. We will read the question one more. In terms of experiment of threads 2 mm apart and limited accordance of two wavelength lambda 1. Okay. What minimum distance from center bright fringe on the screen to meter from the will a bright fringe from one interference will coincide with a bright fringe from the other. Okay. Oh, nothing. Here, it at some point, I'm taking any point, some point, bright fringe of bright fringe from first light source. Okay, is coinciding with bright fringe of second light source. Okay, I don't know what is a number or anything. I just know from these two, it is coinciding because then the y will be same. Actually, our experiment is this is a setup. This screen. If two bright fringes are have to coincide from two light sources, here suppose here the bright fringes form. This y will be same for these two light sources. Then I can write y is n lambda d by d. So this will be same when it coincide first bright fringe with the light source of second. So I can write n1. I don't know which number, which order, or at what maxima is coinciding. N lambda d by d, which is equal to n2. This also I don't know which number is coinciding. This is lambda 1, this is lambda 2, d by d. Okay, something here I can cancel. N1 lambda 1 is equal to n2 lambda 2. Then I will write n1 by n2 is equal to lambda 2 by lambda 1. Here I think we have values. Yeah, lambda 2 10,000, lambda 1 12,000. This I can cancel. Oh, 5 by 6. Okay. Five by 6. That is here 5 by 6. That is I can write fifth maxima of fifth maxima of lambda 1 will coincide with the sixth maxima of lambda 2. Okay, yes, then 5 into you can write 5 into lambda 1 should be equal to 6 into lambda 2. Okay. Then let's check it. 5 into 12,000 and 6 into 10,000 into 10,000. Okay, this is the same. So this is the answer. Here some options are there. What are the order of I mean, what are the numbers of n1 and n2 values? So n1 will be 5, n2 will be 6. Hope this problem is clear. The thing, we just equate the y. If you want to coincide something, then the y should be same. If y should be same, then we can equate the y equations. Then we can get a ratio of lambda 1 by lambda 2. From this, we can found anything. Okay. Next, I am introducing another topic called another modification. Not new topic, another modification. In this modification, I am discussing. In this modification, I am discussing optical path and also how 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 the YDSC experiment is changing when an extra glass law or any optical transparent media, how the pattern is changing if we introduce an extra material into the YDSC experiment. Okay, so I'm going to the optical path. Optical path. What do you mean by optical path? It's a good question. What do you mean by optical path? Optical path is nothing but if a okay, so I'm continuing with optical path. What do you mean by optical path and geometrical path? Is that same? No. Optical path and geometrical path is not same. But in some situation it can be same, mainly in the case of air. If there is another media of another refractive index, then the optical path is not same as geometrical path. I can give an example. So here I have a source as S1. Here another have a source S2. So this is my small length. Small length, two equal lengths L L. Here it is air, and here it is a media of refractive index mu. Okay, so at a time t, the time t, here the velocity will be v is equal to c by mu. Okay, in this media, if the light is traveling with this and these two different cases. Okay, so in these two different ways light is traveling, here the velocity, here this is air, this is a media. So here the velocity will reduce to c by mu because mu is the refractive index of this medium. Then I'm finding the time delta t to take reach here. Okay, so delta t will be this is a thickness, so thickness t or L, same L by V. V is C by mu. So this L mu by C. Okay. So time to cover this distance of the second source by this glass slab is this amount of time. L mu by C. This is a time. Okay, to just reach from here to here. Okay, just reach from here to here. It take delta t time. In this delta t time, how much the light ray will travel in this case, in the first case? Here. In this case, light ray will travel at a distance d is equal to c into delta t, because here velocity is c into L mu by c. So, and it is not the L, it is, please note it down. Okay. Someone will read it as a division. See, first, just listen here. In the second case, a media of refractive index mu. So the light ray has take delta t time to reach to cover this whole glass slab only, to travel a distance of L. It take delta t time, but at the same delta t time, a light source, a light wave, sorry, a light wave through this air has traveled at a distance of L mu. It is greater than this. So the light ray traveled up to here at the time of delta t. So, but the time is so stable. So there is an extra phase. There is an extra phase of delta x distance travel. There is a lag of delta x. If okay, so after this, after there's a screen, if the light ray wants to coincide at a point here at the screen, the light ray will want to coincide the screen. This has to travel an extra delta x. This has to travel an extra delta x for this second. It will travel here, but if you want to cover the screen, it has to travel an amount of delta x. Okay, that is the case. So now I hope it is clear how the optical path concept is coming, how a glass slab is introducing a path difference. So in most of the case, optical path will be mu times geometrical path. Optical path is mu times geometrical path. Okay. So next I'm going to introduce that glass slab in the YDSC experiment. Okay. So I'm going to introduce a glass slab in the YDSC experiment modification. Modification of YDSC. So this is my light source. This is my central O. So light ray can, if there is no glass slab, light ray can pass here. No glass slab, light ray can pass here. So like this. Here a central bright fringe is forming. So now the case is, I'm introducing a glass slab. I'm introducing a glass slab here. Okay. So, what will happen if we introduce a glass law? So, my glass law is this. Okay, here I am just leaving. So, light ray is reaching here. Here, light ray is passing. Okay, is it right? Here I can observe a dark bright fringe as in the case before. I will say no. Then why? Like this we have to study physics. I'm saying if I introduce a glass law, is it possible to get a central bright fringe here? No. Then the next question you should have asked why? Yes. What was the condition for central maxima? Delta x should be 0 for central maxima. Delta x should be 0. Is it right? Here delta x is here if path differences geometrical path is same. I will say geometrical path is same. But this is not the case of optical path because here there is an extra medium of glass slab of mu refractive index on thickness T. This is not the same not the simple case. Yes, we are saying the central maxima for central maxima this delta x should be 0 and due to the introduction introducing after introducing this glass slab of thickness T and refractive index of mu, we won't get a central maxima here. Then asking why? Because why? Because here after introducing the glass slab, delta x is not 0. That is the case. We answer it why. Then another question. How? First question? No. Answer is no. Then we have to ask why. Why? Delta x is not 0. How delta x not 0? Due to this glass law. This glass law, this glass law will write this glass law will create an extra phase shift of mu minus 1 t. Okay. This glass law will create an extra phase shift of mu minus 1 t times. How it is coming here? Okay, I think I haven't did this. Okay, then I will do this. Why we want to skip that? Yes, here I am introducing this slide because I want to you guys should know what is the path difference here. Here we have seen due to delta t time it will travel an extra amount of L mu. Okay, here L. So what will be the path difference? Path difference. What will be the path difference? Path difference delta x is mu times L minus L, that is L into mu minus 1. Simple. This L can be T, the thickness. This L is how much is the either geometrical path or how much is the thickness. Along. So here in this I have, yeah, here this thickness T. So here this glass slab will create an extra face. This is not face, it is path. Oh, extra path difference, path shift of mu minus 1 times T. Okay, so okay, after this it is clear. We won't get a central bright fringe here. Is there any possibility to get central bright fringe? Is there any possibility to get that central maximum fringe anywhere in the screen? Yes. My next question is it possible to get a central maxima anywhere in the screen? Answer is yes. Answer is yes. So this is my screen. Oh, okay, this is my screen. This is my slate. Here I have introduced a glass slab of mu and T. So my source here is the first line, second line. What is the issue here? Here the issue is an extra amount of phase difference. Okay, of this S1 ray. The extra amount of phase difference of this X1 ray. We need only delta X is 0. Okay. To get delta X equal to 0, this first ray having an extra amount delta X. So there is a possibility if the S2 ray, the ray from here, is traveling an extra amount delta X, then the delta X, the phase difference between these two, S1 and S2, will be 0. I think you didn't got anything. Okay. This is my sender row. After passing through this glass slab, it has extra delta X. If I am considering this position, okay, I'm considering this position. Just assume I'm considering this position. If the ray want to reach here, this has to travel a small amount. This want to travel somewhat big amount. Then also the delta X won't be 0. This delta S is getting increase because S1 ray already having an amount of delta x, and again it is traveling more distance. So this is not the possible case. I want to travel this S2. I want to travel this S2 at somewhat big distance. So I am considering a point above the O point here and here. This is my new observation point O dash. According to geometry, okay, here already having a phase shift. Here this ray wants to travel extra amount. Okay, if we consider a line after this geometrical path length 0, but this S2 has to travel somewhat at an amount here. If this delta x traveled by this S2 ray, if this delta x traveled by the S2 ray is compensating this path difference of this glass slab. Okay, if the delta x traveled by the S2 ray is able to compensate the path difference caused by the glass slab, then the central maxima will get. For the central maxima only we need delta x is 0. This two phase difference should be 0. The difference of phase should be 0. That means this should be in equal phase. Okay. For equal phase, both should have same phase. So this want to travel extra. So this delta x. So this delta x should be equal to the path difference caused by this delta x should be equal to the path difference caused by the glass slab. That is mu minus 1 times thickness. That is mu minus 1 times the thickness. Is it okay? I hope it is okay. What is delta x? This is d. What is delta x? Delta x is the delta x is d sine theta. So the delta x is d sine theta. For small angle theta, sine theta approximately equal to tan theta. Then tan theta I can write this new position. I will take y by d. Okay, y by d. So I can write mu minus 1 times thickness is equal to yd by d. So what will be my y? Mu minus 1 times d by d. This will be the position of my central maxima. Right? Position of central maxima. This is a position of central maximum. Okay, so due to the glass law, we got a shift of central maxima to a new position at a distance of y is equal to mu minus 1 t times d by small d. This shift, okay, this shift mainly occurs if you put the glass slab above in the top slit, then the shift towards the top direction, towards the glass slab direction. Okay, then I want to point out something. Then what will be the position of the coming first bright, second dark, first dark, etc. Nothing will change. Nothing will change in the position of other bands. Okay, sorry. It will change by an amount of this. So the first bright fringe will be first by lambda d by d, not from the O, is from the O dash. So mu minus 1 a times d, because this equation was valid for central fringe is at O. This is a screen. This is O. Here was a central bright fringe. But now it is shifted to new position O dash of amount y. This y is equal to this. So the new fringes, the new fringes will count from here. So in the every fringe, an extra amount of mu minus 1 t by d. Okay, then what will be my second bright fringe? This will be 2 d lambda by d plus this mu minus 1 d by d. Similarly, third of bright branch, here 3, this time will be same. Okay, so what about the dark fringe? Similarly, nothing changed. y1d dark fringe, first dark fringe is d lambda by 2, d is already there. Then an extra amount of mu minus 1 times td by small d. So what will be my second dark fringe? This is 3 by 2 d lambda by d plus an extra amount of mu minus 1 times td by d, and so on. Okay, so I hope this is okay to everyone. I think we just modified this path, optical path. We got a new concept of optical path when a glass slab or any slab of thickness t and different refractive index, the light ray wants to travel an extra amount apart from the geometrical length. Then path difference, we have found an expression for path difference. Okay. Then we move into modification of IDSD. Modification of IDSD is as follows. We have introduced a glass slab here. Then is that central bright fringe is at O? No. First question is central bright fringe is at O. Answer is no. Then why? Because delta x is not 0. For central maxima, we know delta x is 0. But the glass slab will create an extra path shift of mu minus 1 times t. Then we move on. Is there any possibility to get a central maximum anywhere in the screen? Yes. Where when the path difference of mu minus 1 t is compensated by the second ray by an amount. Then we move to the equation. We got the equation. The new central bright fringe is at this position mu minus 1 td by small d. Then corresponding changes. Then I want to do one problem. So yeah. Okay, in this problem, what they are saying. This problem, in the YDC experiment, find the thickness of glass slab. A refracting distance given. It should be placed. We should be placed before upper slit S1, so that central maxima now lies at a point where the fifth bright fringe was lying earlier before inserting the slab. Okay, then the wavelength. Wavelength of light is used 5000 Angstrom. Okay, lambda is given as 5000 Angstrom. That is okay. Mu is given 1.5. So the central maximum lies at a point where the fifth fringe. Okay, fifth bright fringe. Oh, fifth bright fringe. So the position of y is n lambda d by capital D. Then the new central bright fringe is at fifth position. That is mu minus 1 t times capital D by small d will be equal to lambda d by d. 5 times lambda d by d. Cancel this. What do we want? Find the thickness. Mu is given as 1.5. So 1.5 minus 1. The thickness is 5 into 5. So 5 into 5000 into 10 to the power minus 10. So Armstrong to meter conversion, just multiply by 10 to the power minus 10. Answer is okay. So 0.5, that is 5 by 10 times t is equal to 5000 into 10 to the power 10. And 5 will cancel. This 3 zeros, 1 more 0. So t is equal to 5 into 10 to the power minus 6 thickness. Okay, this will be the thickness of glass slab. So thank you, my dear friends, for my lecture who patiently waited. So thank you.